It's my pleasure to introduce my friend, colleague in the department, Dr. Laxmidhar Behera. He is the Associate Professor in Department of Electrical Engineering at IIT Kanpur. He obtained bachelor's degree in 1988 and master's degree in 1990, both from Electrical Engineering from Regional Engineering College, Rourkela, and PhD from IIT Delhi in 1996. On the topic neural controllers for robot manipulators. He has been a guest researcher at the Fraunhofer Institute of Autonomous Intelligent Systems and Real World Computing Partnership, AIS.ART.
Okay, what is my the overall goal of this lecture is that in one way we are looking at constructing the quantum computer, and the other hand we are interested what kind of problems we would like to deal if we have a quantum computer. So I am going to this second category, that I am looking at information processing problems. So one of my students is working in this particular area now. The problem is a machine, it has to understand a chapter and then it has to answer the questions at the end of the chapter. This is the number one research problem in AI. It's unsolved, very difficult, and I will just focus what is the problem. Similarly, another work we are also doing is real-time redundancy resolution in a redundant manipulator. Like I have a hand which is redundant, and like for example I want to touch my nose, I have unlimited ways by which I can touch my nose. It's not unique, so many ways depending on the environment. So the problem there is when the hand is redundant, you can perform the same task in infinite number of ways, theoretically speaking. So then how to select the right one that has certain meaning given the context. Similarly, we have a multi-agent system, and where there are cooperation, like at present I am in a sabbatical in University of Ulster, and in the laboratory there is a powered floor and around 20 mobile robots are continuously moving in that, and continuously they are exploring the environment and they are learning among themselves how to cooperate, either for some kind of group task or their own individual task. Like let us read a simple narration. Like once upon a time there lived a ferocious lion in the forest. He started killing animals in the forest indiscriminately. The animals gathered and decided to approach the lion with the offer of one animal of each species volunteering itself to be eaten by the lion every day. So every day it was the turn of one of the animals, and in the end came the rabbit's turn. The rabbit chose a old among them, and this rabbit was wise and took its own sweet time to go to the lion, and the narration goes on. So although this, when we read this story, we easily seem to understand it, the semantic information processing that is going on within us. We have very little knowledge, but we are very capable of doing it. Whereas if I give this particular text to the machine and ask the question, for example here, the question is, what is the summary of this particular narration. Like, as you know, that if the story ends, the rabbit finally traps the lion in the well. Particularly in Indian context, this is a pretty well-known story. So the theme of the story is that the wisdom is more powerful than the brute force. Now, we ask question to the machine that can it answer what is the theme of this story? Okay, that's of course the most difficult one. Before it can answer this question, now I would ask the machine, that is provided this particular text, and I ask the machine the question, can you identify the main events in this story, in this narration? Like, for example, one of the main events in the beginning is that lion started killing the animals indiscriminately. Lion naturally kills animals, that's not surprising. But when it started killing indiscriminately, that becomes an important event. Similarly, the rabbits choosing the oldest among them. So like that, you have to have some criteria by which you select these important events. Now think of, we are reading a novel. You have so many sentences in that. And then the machine will read the entire novel, and then it has to answer the questions. So the amount of information, because what we are looking at, this information explosion in this. And more than that, which at the end of this lecture I would discuss, is whether we have a present classical computer, or the way we are visualizing the quantum computer, we are still doing the symbol processing, not semantic processing. So that's again another problem we need to address. Another example here is, this is a verse from Bhagavatam. It says, Atma Ramasya Murayo Nirgrantha Pirukrame Kurvanti Ahitukim Bhaktim Itham Bhuta Guna Hari. And this is a verse from Bhagavatam, and it has 60 different meanings, at least more than 60 different meanings. And this particular book has 18,000 verses. And you have to derive as one of the meaning, at least the most appropriate meaning, given the total context of 18,000 verses. So what I'm trying to tell, the information explosion that's happening when I have to derive a appropriate semantic meaning. And it's very, very difficult problem. So the question is that, can we solve this? Before that also, let me also. You see, there is a yellow bulb, and the robot is trying to reach in many possible ways. And I know so as I said in the beginning, some of the information processing problem. So what we saw that this manipulator is trying to reach the same target, and it can reach in multiple ways. And this multiplicity is not some finite number, with given the number of links you increase, the number in which it can reach the same target is actually theoretically infinite. Now, how in real time we compute a feasible solution? Okay, at the moment, the researchers, how do they implement? They do everything offline. They specify a task, beforehand they plan the redundancy resolution and exactly find one solution, and everything is done offline. You can't do real time. So, that is the challenge. Similarly, when I talk about quantum computational intelligence, there is I think it has been now 3 consecutive years, a quantum interaction, a specific conference is going on, and this time it is being held in Germany. And the idea is that how can we bring in the ideas from quantum mechanics or use the quantum ideas and improve the performance in information processing. So, that is what when I say quantum computational intelligence. So, there are, of course, these are not the, I have just identified some of these: quantum neural networks, quantum associative memories, quantum Bayesian network. This is what is one of my students is working in solving this book chapter understanding. Quantum fuzzy networks, quantum evolutionary algorithm, quantum games, quantum agents. So, there are many such areas people are just working on. The ideas have not been concretized, and as I apologized in the beginning of the lecture, I wanted to do a proper review, but somehow I really could not find time to do it. And I will just present some of the work that we have. Actually, some of these things I have presented, but I'll again repeat those things. One is quantum neural network. The approach that we have used is we use the quantum probability concept, and you use this quantum probability concept to solve some of the problems in control, stochastic filtering. So, idea is like this, that you have a single stimulus and goes to multiple neurons there, and these are special neurons, and then you have a collective response that is it is like you can think about a photon hitting multiple slits, and then you have a collective response. You can think in that way, and the idea is that when we do a stochastic filtering, the main problem is how to find or how to estimate the PDF associated with the signal, the probability density function. And because given a signal, if I know the PDF associated with it, then the solution is almost known. But because we do not have a way to estimate this PDF, we use many ad hoc techniques, assuming a priori knowledge about the signal as well as the noise type. So, I just give some idea here. So, what is this? This is my stochastic signal, and this is my network, and this is a Schrodinger wave equation, and this network, this network outputs, these neurons, they are all specially located, hence they set up a special potential field, and in that field we can assume that a quantum object, its state is being evolved, or it excites a quantum object, and then we do some kind of processing there in terms of estimation of the signal, and there is an error corrector loop. And of course, we design the learning algorithm for these weights of this in such a way that the actual the PDF associated with y, the PDF is actually, if you see that probability amplitude in the psi function, that contains the information about the probability, as we know. So that is the objective here, and these are the details. I will not go in of that. So some of the results Like if I have a signal, DC signal with noise embedded, then we see that how signal is being tracked, and once it goes there, you see that here how the initial wave packet, and this is at one instant of time, and finally the wave packet is fixed here. This is a linear modulation of the neural network. So when you do nonlinear modulation, so here you see that this is a signal, is a complicated signal, is a amplitude modulated signal, and this signal is also embedded in 20 dB noise, and this has been filtered pretty accurately. Similarly, a square wave, and now when we use a nonlinear function here, that means this neural network, we use a nonlinear kernel there, then you see here it's even more interesting because the signal is being tracked, and here you look at how the wave packet is moving. That is, this is my initial wave packet, and my signal strength is 2, and you see that wave packet, corresponding to the Schrodinger wave equation, it is moving towards the signal. So at some intermediate interval it is here, so that is here, this particular point, and when it is at this particular point 3, this signal is already it has already tracked the signal, that is, it is a DC signal of strength 2, and hence even if you add, you see that the noise is too much, but still it is unperturbed, means the process is very robust. Similarly, if you look at this sinusoid signal, and we have taken these 3 instants, 1, 2, 3, and once you do the information processing and learning, and then you see that how the PDF associated with this 3 point are being learnt here. You see that at this particular point, because this Gaussian noise we have added, you see that amplitude strength here is 0, and it is a Gaussian. So you see at that particular point, this is my PDF with 0 mean, and then at 2, which is the positive signal, and you see that the mean almost is 2, and there is a Gaussian packet associated there, and at 3 again the signal is -2 with a Gaussian noise packet. So okay, and this is something interesting. You see that now if you compare the Kalman filter and the present approach, you see that when 0 dB noise means very high noise, the Kalman filter starts degrading there, whereas this approach remains almost invariant. There are various QNN models in the literature. One is Altaisky model, where the input and output qubits can be implemented by optical modes. Anyway, this is can be implemented by optical modes with a different polarization. The weights of QNN can be implemented by optical beam splitter and phase shifters. But anyway, this Altaisky model is the neural network, the weights, they are quantum. That means they are complex quantities, and so it's a different approach than what we have done. Similarly, in Baermann's model, quantum dot molecules of different polarization, the system, and the quantum dot is an object carefully engineered to behave according to the rules of quantum mechanics. Similarly, Chursley model system, a barrier with slits in front of a photosensitive plates, that is just like I showed you that we have a multiple neurons, and if we consider them multiple slits, then our model will converge to this model. Okay. Then this is about neural network. Then let us talk about quantum memory, associative memory. So associative memory is a problem. You first memorize the patterns, and then no, they're all different. They're all different.
So we can use the other types also.
Yes, there are various schemes. Yes. This quantum associative memory. Associative memory in general is a problem where we have multiple patterns that we memorize first, and we have to have a method of how to memorize, how to put those patterns or store in the network, or the network has to be coded in such a way it recognizes or it knows that these are the patterns it has stored first. And second, when a desired pattern is presented to it or the partial information of that, then it should be able to tell us that this is the pattern, right? So pattern storing and pattern retrieval, when both are done simultaneously, then we say it is a memory. It is not simply enough that you put in the memory, we must know also how to retrieve from the memory the pattern. So that is associative memory. So what is the problem? Like the Hopfield network is the first network that that is the model of associative memory. But the problem with the Hopfield network is that as you store a pattern, and almost the anti-pattern is stored also in the network. So that means the capacity of the network goes on decreasing as you try to store more and more patterns in the Hopfield network. So and that's why the problem of spurious patterns is pretty much there in traditional Hopfield network. So so there are certain these things. J.J. Hopfield first explored the idea of associative memory based on collective computation on neural networks. Kusko introduced the concept of bidirectional associative memory. Maximum number of binary patterns that can be stored in Hopfield network of n neurons is 0.14 n. That's a pretty small number. Okay, P max. For BAM, the maximum number is also less than n. If you have a n-bit neural network, when n unit n neurons are there, the maximum number of patterns you can store is always less than n. So with various possible improvement, the maximum number remains linear in the number of neurons. Okay. So the classical associative memory has a limitation of storage capacity. So what is then the basic idea in quantum associative memory is that let us think about simply a 2-bit qubit register. Obviously, maximum patterns we can store here is 4. But and whereas these coefficients, square of them, add sum is equal to 1. So what is normally, if I have a n qubit register, I can store 2 to the power n number of patterns. But normally we don't store that many. We store number of patterns much less than 2 to the power n. So obviously, what should look like for example, if I store using 2 qubit, say 2 patterns, then these coefficients, they should be as small as possible, and these coefficients should be as large as possible. Just basic idea. And then there has to be some, okay, here is the problem. That is, you start with this 0 state, all 0 state qubit register, and find out an operator that would transform this one to the pi is the required pattern to be stored, and like that I have capital P number of patterns. So, the so that is the storing problem. How do we store? So, the problem lies in how to find out this quantum operator OS on this, such that this operation this map can be achieved. And similarly, when once it is stored, so this is my quantum register state now. Now, what should be the operation on that? Then the desired pattern is retrieved. Okay? So, that is the problem. Okay. So, some of these operators that are normally used in designing a quantum associative memory, of course, this is a very popular bit flip operator. Like that, there are many operators used, those are not and of course, just like in Grover's search algorithm, we use an oracle information. Similarly, we also define an oracle for the number of the type of patterns that we have to store, and then we use like this is, I think this is the Grover's algorithm, that you have an oracle, and then you have the operator, Grover's operator, inversion about mean, and then let me, because some of you already must have heard about it. The algorithm is like that. You start from all zero state and then all equiprobable states. Okay, that is every state is equiprobable here. So that's the beginning, and from there through oracle operation we identify the state that we are looking for, and then when the state that which is desired, the sign becomes negative, and then apply the inversion about mean, so that the amplitude associated with the desired one goes on increasing and the others goes on decreasing, and then repeat step 2 and 3 step 2 and 3 r times, and finally make a measurement. And as you know that quantum computation is a probabilistic one, you don't get a definite answer. So the probability of getting measurement result is this one, where r is always root over n. So this is Grover's result. So if I explain to you graphically, what happens is that we go to this particular state where each base states or each possible solutions, they are associated with same probability amplitude, and then the solution bit gets negative through oracle operation, and then using inversion about mean, the solution amplitude goes on increasing. So this is a graphical representation of Grover's algorithm, and in fact the same thing we can use to design the quantum associative memory. I will not go into details of this Ventura's algorithm. The Ventura, they are the first to design a quantum associative memory, and then this is in their thing, this is the upper bound on probability of desired state. This is their result. Then this is the Trugenberger's approach. So this is something we did. We simply used the Grover's algorithm, and what we did is that this is our desired state. Means these we should start from all all zero state to reach this. We have p number of pi patterns, and that has to be stored. So what we are doing is, I think I have only written this summary. So, start with all 0 state, make it equiprobable for all basis states by applying Hadamard operator, use oracle operator to recognize those patterns which correspond to the patterns to be stored, apply inversion about mean, sorry there are double mistake, operator to increase the probabilities of the recognized patterns. After refuting oracle and inversion about mean operation, we showed that we can reach this, and we have found mathematically what is the probability of storing them, and that I will show you the result. So, we found that the total probability with all the undesired patterns are this much, and for large n, which is generally the case, that means n is the total possible number of patterns, that is 2 to the power n. So, when this n is very large and p number of patterns that is to be stored is comparatively much less, then you can see this probability can be assumed to be very less. So, the idea is here is that again we have say these are the equiprobable states, and these are the desired states. Means we using those two performance we can actually reach this particular thing. And similarly, the retrieval, instead of using the original Grover's algorithm, we just change this particular operation, and then we are able to show that number of steps required to retrieve is order of root over p. So, that if p is the number of patterns that is to be stored, the analysis shows that the computation time that is required to find out which is the pattern to be retrieved is the order is root over p, is similar to that. So this is so the objective is that I have 3 patterns here, and the pattern that is to be retrieved, if this is 1. So, finally, you see that this has the max highest probability, and this other 2 desired will have comparatively much less probability. And the analysis that has been done, this is the probability that we get without considering the effect of spurious patterns. The probability of getting a desired pattern is given by this, using this method, and due to the effect of spurious patterns, the actual probability, this one, will be reduced, and this has been derived. So, if you look at the computational the comparative analysis in Ventura's and Truzenberger's approach, the order is Pn, and whereas in the proposed approach this is root over n by p. So, p is number of patterns and n is number of bits. For example, if n is 2 to the power 64 and p is 2 to the power 30, then the first case the computation is order of 2 to the power 38, whereas using a simple approach, I am not saying that we have done something very big, this is simply a preliminary work, and still you see that the order is much less here. This is an idea, one of my again PhD students who is working on quantum evolutionary algorithm. Those who are working on evolutionary algorithm, you know that is very popular as simple genetic algorithm, but there is another approach which is probabilistic, purely probabilistic. So, what is the meaning of that? Like you have a what happens in evolutionary algorithm? We have a population of solutions, right? Initial solutions. So, let us say these are the solutions, initial solutions. And what we are interested, using a fitness criteria to prune these solutions and find out in a manner of evolution what is the best solution. So, one of the approach is univariate marginal distribution algorithm. And what this univariate marginal distribution algorithm does, let me explain the theory first, is that probability of the distribution of string, okay, probability of distribution of string, each let us say I have n bits there, and this n bits represents a specific solution, and the distribution, probability distribution of that string Px in UMDA can be represented product of individual bit in the string. So, like if I have in the previous one, if you see here, I have what I am looking at to estimate the joint distribution of these 3 bits. If I know, then I can generate probabilistically these strings. But how do I estimate that? One of the ways is, if I assume that the probability distribution of these combined 3 bits is simply product of individual probability distribution of individual. That means they are independent of each other. That is the simplest way I can try to solve this problem. So, if we do this, then the easiest way, let me not go to technicality, I can just explain to you. Let us say I have some 3 populations here, and I am saying that this event this is independent of this event and independent of this event. So, like when I optimize a system, let us say I have n parameters, if I assume each parameter is independent of each other, then it is all right. Okay? This assumption is all right, valid. And then I see the frequency of 1s and frequency of 0s. Like frequency of 1 is this marginal frequency which we say P11 is 1 by 3 here. Similarly, here P1 is the second string, second bit is 2 by 3, and of this is 2 by 3. Okay? And then I am saying this is the assumption in univariate marginal distribution EMD algorithm, that probability of x1 equal to 1, x2 equal to 1, and x3 equal to 1, this distribution is P11, P11, P21, P31. That is the, but this is not the actually true thing. This is a very simplified thing. If we assume that these are the question is that can we, the difficulty is that because as we optimize a system, all the time we are generating the solution, and when we go to the fitness, we get some idea about what the nature of the solution. So, what we are now trying to do is that we are using quantum probability and trying to estimate this P directly using the concept of probability, quantum probability. I will I will just show you some of these works are already been done in quantum evolutionary algorithm. This is quantum inspired evolutionary algorithm, a multimodal EDA. This work almost has done the same thing that I just explained to you. They are also doing the they looked at first the probabilistic way of generating this population. So, the problem here is how do we estimate EDA, estimation of distribution algorithm. As I said you in the beginning, even in the stochastic filtering, the big problem has been to estimate the probability density associated with it. Okay. This is the information. So, what quantum ideas interesting in this concept is how do we, can we create a computational learning architecture in which these distributions are naturally learned. Okay. without assuming any a priori distribution, which we do in classical thing. So, that is the basic idea. This is another work, quantum inspired evolutionary algorithm for a class of combinatorial optimization by Han and Kim, and this is a recent paper also, quantum genetic optimization and this. But the approach here are almost here. Let me give you what is this paper focuses. This paper, what it does is that it considers the strings as qubit. It is not what the focus of this paper. Focus of this paper, what I just explained to you, how do we estimate the distribution algorithm. Whereas these two papers, what do? They give diversity to the population generation. Like when I look at a solution should be as diverse as possible. When we look at the initial population, I cannot guarantee that this is actually diverse in the sense that, in all corner, in all dimension of the solution space, at least is represented in the initial population. So, how do we maintain this diversity in genetic evolution? So, these two papers, they give that kind of idea, how to introduce diversity using quantum idea. Okay, that's actually my talk. I didn't want to speak more because I didn't do. Conclusion is the quantum ideas can be used to develop quantum algorithms to solve many types of problems in estimation of distribution algorithm, which is actually my primary focus, and quantum design automation and robotics. But one of the things that I would like to ask, and I have been asking myself, and I don't have an answer, is that can we perform semantic information processing? What do I mean by semantic information processing? Like you see that this is a hard disk, right? And if you look at our classical mechanics, this is simply a rigid body. It has no meaning, right? But you see that in everyday real world, this can be used as a paperweight, right? It is a hard disk. It has various meaning when I manipulate this object. So, semantic information is something is very, very, because as we are, working on this book chapter, this narration processing using a computer, we are stuck with this problem that unless we develop a method of, or a physics of semantic information, what I would say that the physics of semantic information, that because whether it is a classical computer or a quantum computer, we are still looking at simply symbolic manipulation. The symbol is simply an object without any meaning. But meaning is there. Even, for example, the structure, this object has its own meaning. Okay? Whether I use one language, use another language, but it has a certain, because everybody can say this is a dice.
We have some time for a couple of questions. Yeah, sure. Go ahead, please.
Evolutionary algorithm, that you showed that the three solutions, which are the solutions of the same problem, but then you were saying that each are independent. What is the meaning of that? They are independent of each other.
Oh, okay. The point is that when classically, see, this estimation of distribution algorithm is a very difficult problem. There are various ways, Bayesian network and various approaches people follow to do this. So, UMDA, what it does, it simplifies the problem. Like suppose, for example, I am looking at distribution of 3 events, and let us say they are dependent on each other. They are dependent on each other. Like, for example, I am tossing a coin. Okay. And if I am tossing two coins separately together, let us say. So, if I am tossing a coin first and I am tossing a coin again another coin, so I can easily see that this coin tossing and the other coin tossing can be assumed independent of each other. But normally what happens is that when we are looking at a practical systems, like I have let us say I am trying to design a particular table, and length and width and depth that has to be optimized for a certain problem, right. So, they are dependent on each other, these events. So, when we try to estimate the distribution, probability distribution of each parameter, okay, so they are dependent on each other, but in the UMDA I am doing this coin tossing problem. I am assuming each parameter event statistically is independent of another parameter.